Today we're looking at projectile motion. Motion of a particle when going through the air, acted upon gravity and air resistance. We call this projectile motion. So in modeling the projectile motion, the following assumptions are made. So we assume the projectile, no matter how big it is a point particle. We ignore the air resistance. We assume the Earth is flat. We ignore the rotation of the Earth, and we ignore variations in gravity due to height. So gravity actually becomes less powerful the further you get away from the Earth's core. However, we don't accommodate for that because there's such little change in the height and in the gravity, therefore, when comparing it to the radius of the Earth, which is such a huge value. These assumptions are generally valid for projectiles moving close to Earth's surface at heights of no more than approximately 200 meters. So if we consider a projectile fired in a vertical two-dimensional plane from the origin O, so that's this point down here, it has initial speed vector v meters per second at an angle of alpha to the horizontal. T is our flight time, h is the maximum height reached, r is the range on the horizontal plane, which is the total horizontal distance traveled. So the only force that's acting on the projectile is the weight force. So that's the force due to gravity. Acceleration is gj, but it's going in the negative direction. So that's negative gj. So that's this vector over here. So that's constantly acting upon our projectile. The time of flight is the time that projectile takes to go up and down again, or the time at which it returns to ground level. So that's when the vertical component of the position is equal to 0. Maximum height occurs when the particle is no longer rising, i.e. when the vertical component of the velocity is equal to 0. So the vertical component of that. And that makes sense, right? Because to change direction, at some point you have to stop. You can't just instantly turn around. So in general, the time that the projectile will be in the air will be twice this amount. So it takes half of the time to get to its maximum point, and then the other half to get to the minimum point. So that's twice the amount to make the total time in the air. So looking at example 12, a golf ball is hit so that it leaves the bunker at a speed of 35 meters per second at an angle of 20 degrees to the horizontal. State the initial velocity vector of the ball. So we've got v initial, that's going to be equal to, now it's 20 degrees to the horizontal, our magnitude is 35, so we're just converting that to instead be in Cartesian form, so that's going to be 35 cos 20 degrees I plus 35 sine 20 degrees J. And that is equal to, in decimal form, 32.889 I plus 11.97 J. So that's our initial velocity vector of the ball. Determine the velocity of the ball as a function of time. So that's our initial, but we want to say what is the velocity as a function of time. So for that, we need to use the fact that v is going to be the derivative of the acceleration vector, and the acceleration vector is just going to be with respect to gravity. So acceleration is equal to minus 9.8 j. So v equals the integral of minus 9.8 j. But then we also have, and I'm going to write this to the right, also that's dt, the integral of 0 I dt. So what that means is that our horizontal velocity is going to be a constant. Because if you differentiate a constant, you get a value of 0. So when we anti-differentiate 0, we're going to get a constant value. So this gives us, let's call it C1 I minus 9.8 Tj. So that is our velocity component. Well, how are we going to find the value of C1? Well, we know that when t equals 0, oh, sorry, I forgot my plus c in my j component. So because we're integrating negative 9.8, we're going to get plus negative 9.8 plus cj. So we know that when v of 0, that's our v initial, which is going to be 32.889i plus 11.97j. So we can do that to solve for our value of c. So c1, let's call this c2. C1 is a constant because I wrote an I component next to it. So C1 is equal to 32.889. And then C2 is going to be equal to, so 9.8 times 0 plus C2 has to equal 11.97. So that's just 11.97 itself. So the velocity of the ball as a function of time is going to be v of t is equal to 32.889i plus negative 9.8t plus 11.97j. So that's our j component. Part C. Determine the maximum height that the ball reaches and the location of the maximum height from the bunker. So maximum height, max height, is when v of t is equal to 0. So v of t is going to be equal to, it's going to be 32.889 in the I, because we don't care how far it is. We're just caring about the height. So 32.889 is going to have that constant velocity in the I direction, but we want our negative 9.8 t plus 11.97j to be equal to 0. We want its vertical velocity to be equal to 0. So that's when j component is equal to 0, because that means it's slowed down to a stop and it's starting to fall. So therefore, negative 9.8t plus 11.97 equals 0. So t is going to equal 1.22. And that's seconds. Right, so the max height is at t equals 1.22, but we also need to find the maximum, the location of the maximum height from the bunker. So we want to find the I and j components when t is equal to 1.22s. So for that, we need to find our x of t. So x of t is equal to the integral of v of t, which is going to equal 32.889 t plus c3i plus negative 4.9 t squared. You're going to get very used to this whole negative 4.9 t squared. It comes up a lot because it's the second derivative of gravity. The second integral of gravity. So then we're going to have plus 11.97 t plus c4j. And so we're assuming that the bunker is our origin. So assume bunker is x of t is equal to 0 when t equals 0. So therefore, this component goes to 0. These two components go to 0. So therefore, c3 equals c4 is equal to 0. It doesn't actually matter what the position of the bunker is because we're asked how far is it from the bunker. So let's just find the location. So we're going to find x of 1.22, which is equal to, in the I component, 40.17i plus 7.31j. So that's the position of x at its maximum, so x of 1.22. I actually used the exact value, which is 11.97 over 9.8 for that. That comes from down here. But even then, I would have had some rounding to get to 11.97. So you might get slightly different values to this. Part D, determine the time that the ball is in the air. So as we talked about earlier, t of max height is equal to half t total. So that's just going to equal our 1.22 times 2, which is equal to 2.44 seconds. So it's going to be entirely in the air for 2.44 seconds. And then part E, determine the horizontal distance covered by the golf ball. That's just going to be the I component of x of 2.44, which is equal to twice the I component of x of 1.22. So it's going to be 80.34. 80.34. And goodness me, I've forgotten all my units. So let's go back up. We're working with meters per second. So that's going to be 80.34 meters. I don't think there's anywhere else where we really need to put in, because we've got seconds there. These are just vectors. I guess for this, you could talk about it being a position of 40.17 meters and 7.31 meters tall. All right, but that is everything for example 12. Moving on to example 13, the next one. So this time our start is at the top of a cliff. So it's different to the last one because we're not launching it from the same height as where it lands. So we've got a projectile fired at time equals t equals 0 from the top of a cliff whose base is taken to be the origin. So our origin is down here. The position vector in meters at a time t in seconds is the projectile of the projectile is given by r of t is equal to 20ti plus 50 plus 25t minus 4.9t squared. So we get that 4.9t squared once again. How high is the cliff top above its base? So for A, r of t, which is going to be, r of 0, because that's at the origin, is going to be equal to, so our I component obviously goes to 0 because we're in line with the origin. Our J component is going to be equal to 50 plus 0, so that's 50J. We know that the position vector is in meters. So this is going to be a 50-meter tall cliff. Part B, give an expression for the velocity of the projectile. So velocity is going to be the derivative of r. So we take r dot t, which is going to be 20i, once again, constant velocity in the I direction, and then we're going to get 25 minus 9.8t in the j direction. So once again, we get that negative 9.8, which comes from gravity. We're asked to give an expression for the velocity of the projectile, and this satisfies that. So this is the same as v of t. Part C, determine the initial speed and launch angle of the projectile. So for the initial speed, we're just letting v of 0, essentially, is what we're trying to find. So v of 0 is equal to 20i plus 25j. Now, we're asked for the initial speed and launch angle. This is currently just giving us the Cartesian form, but we're asked for the polar form, essentially. So the magnitude of v of 0 is going to give us our launch speed, which is, so magnitude is 32.01 meters per second, and our angle alpha with the horizontal is going to be tan inverse of 25 over 20, which is equal to 51.34 degrees. So this V0 magnitude, that's just coming from summing the squares of 20 and 25 and then square rooting the sum. Okay, part D, determine the speed and angle at which the projectile strikes the ground. So we need to know what is the angle and the speed when this event happens. So to find that, we first need to determine when is r of t equal to 0. So r of t, this is part D, is equal to 0, which means looking at our components, the easiest one to solve for, or the only one we can solve for, is this 25 minus 9.8t. So therefore 25 minus 9.8t is going to equal to 0. Take the 9.8t to the other side, divide through. We're going to get 25 divided by 9.8, which is 2.55 seconds. So then we need to find out what is the velocity at that time. So velocity of 2.25 is equal to still 20i, because it's a constant velocity, but our j component is going to be... Oh, I've taken this from my from the wrong value. So I actually need to use 50 plus 25t minus 4.9t squared. That makes sense because we're going to have two values of t. We're going to have a negative value of t, which is if we were to continue this out to here. So that means my value has to be a quadratic. So let's just backtrack a bit. 0 is going to be equal to, apologies for the mistake here, 50 plus 25t minus 4.9t squared. So 50 plus 25t minus 4.9t squared. So factorizing that, if that's equal to 0, so we'll just move this up here. So if that's equal to 0, our values of t using the quadratic formula are either negative 1.53 or 6.639. Okay, so we reject t less than 0, which means our time is 6.639. So continuing through, we want to find the velocity of 6.639 seconds. So velocity of 6.639. So substituting that back in, we're going to get the value 20i, like I said earlier, because it's a constant horizontal, plus 25, take 9.8 times 6.63, which is going to give us negative 40.06j. So we can see that makes sense because we're going to have a negative j velocity, because the velocity is going downwards after the midpoint. And so finding the speed is going to be the magnitude of v at 6.639, and the angle, which is going to be 10 inverse of 40.06 over 20. That'll give us our first quadrant solution, which we can use to find the angle into the ground. So the values of these are 44.77, so that's meters per second. Our angle is 63.47 degrees, but that would be the angle in the first quadrant. We're actually coming down. We're into the fourth quadrant there with positive x and negative y. So this is actually negative 63.47 degrees. So an angle negative to the x-axis. And so lastly, we're asked to find the distance between the launching point and the point where the projectile hits the ground. So that's the distance between x of 0 and x of 6.639. So x of 6.639, take x of 0, which is going to give us a value of, so that's going to be 20 times 6.639, take 0, because we're only interested in the I components. The J components is we answered in the first part, that's 50 meters tall. So this is going to give us a value of, so 20 times 6.639 is 132.78 meters. So that's the distance between the launching point and the point where the projectile hits the ground. Okay, example 14. A basketballer shoots for a goal from a 3-point line. He throws the ball with an initial speed of 15 meters per second, and the ball leaves his hands at a height of 2.1 meters. Calculate the possible angles of projection if he is to score a goal. So then we're given some data. The distance from the goal to the 3-point line is 6.25 meters, and the height of the ring is 3.05. So we want to look at all of the possible angles where this makes 6.25. So we've got, first of all, we want to draw an image. So there's our 2.1 meters. Here's our, well, let's get them on the same plane. 3.05 meters, and we want all of the possible angles that can get it sort of into that hoop area, which is 6.25 meters away. So the basketball must pass through the point where X, which is our horizontal, is equal to 6.25, and Y has to equal 0.95. So what we're doing there is we're letting this 2.1 be the origin, and this 3.05 be 0.95 meters above it. So all we then have to do is use that value of 15 meters per second and find what values of theta can accommodate for that. So we have velocity is equal to, the magnitude of velocity is equal to 15 meters per second. We have so from this magnitude of 15, we know that the vector v is going to be equal to 15 cosine some angle alpha I plus 15 sine of some angle alpha j. So if we were to consider the fact that v is also coming from the fact that acceleration is equal to negative 9.8 j, we know that velocity is also equal to some constant c1i. So this is the integral of acceleration, minus 4.9, just 9.8t, plus c 2j. So let's actually make that a plus in between. And therefore we know that x of t is going to be equal to c1t plus c3 plus negative 4.9 t squared plus c2t plus c4j. Okay, so we have all these constants that we need to deal with. So some things that we know from the get-go is that x of 0 is going to be 0. So that cancels out c3 and c4 for us. So because x of 0 is equal to 0, therefore c3 and c4 are equal to 0. So what we're left with is that x of t is equal to c1ti plus c2t take 4.9 t squared j. Another piece of information that we can use to our advantage is the fact that the x component of velocity is going to be constant at the start. So we know that c1 has to equal 15 cosine alpha. So x of t is actually 15 cosine alpha times t plus c2t minus 4.9 t squared. So we're getting closer to where we want to be, which is having alpha be our only variable. The last bit of information we need is that when t equals to 0, c2 is going to be equal to our initial velocity, which is 15 sine of alpha. I'm actually going to rename this to v of 0 so that that's a little bit clearer what this value actually represents. So we know c2, because t equals to 0, c2 has to equal 15 sine of alpha. So it's going to be 15 cosine, let's actually call it 15t cosine alpha I plus 15 15t sine of alpha minus 4.9 t squared j. So what this gives us is a value for x and a value for y. So what we're going to do is use the values of x that we know we want to reach, which is 6.25 and 0.95. So we know 6.25 equals 15 cosine alpha times t, and we know that 0.95 equals 15 sine alpha times t minus 4.9 t squared. So what we're going to do is rearrange this to make t the subject and then substitute it into here. So t equals 6.25. So if that's equation 1 and this is equation 2, equation 3 is going to be 6.25 over 15 cos alpha. We want to sub equation 3 into equation 2. And what we end up with here is that 0.95 is equal to 15 sine alpha over 15 cosine alpha times 6.25 minus 4.9 t squared, which is actually 6.25 over 15 cosine alpha squared. But we have an identity for that cos 1 over cos squared is the same as secant squared. So this simplifies out to the 15s cancel. We get 10 alpha times 6.25 minus 4.9 times 6.25 times secant alpha squared. And we know that secant squared of alpha is equal to 1 plus tan squared of alpha. So we can actually rewrite this as a quadratic with tan alpha as its x. So this becomes tan alpha, let's actually rewrite this, make it a little bit neater, 6.25 tan alpha minus 4.9 times 6.25 times 1, right? Because it's 1 plus tan squared, minus 4.9 times 6.25 tan alpha squared. Okay, so now that we've done that, we're going to let the left-hand side equal to 0, rewrite this a little bit neater. So I'll do that quickly off screen. Okay, whilst trying to put this off camera, I realized that I missed out of this 15 squared there. So that 15 squared is going to be carried throughout there. And what we're going to get is 0.8507 as our A term. So negative 0.8507. Our B term is positive 6.25. And our C term is negative 1.8007. So that means 10 alpha is going to be equal to either 7.0465 or 0.3004. So that's just applying the quadratic formula with a value of A, B, and C as such. And so what this means is that alpha has two possible solutions, which is the inverse tan of both of those, which is 81.92 degrees, or 16.92 degrees. So there are two possible angles of projection that will get that basketball into the hoop. That's all for this video. Thank you very much for watching.